estimated carbon footprint of geothermal ranks from 12 to 20 grams per kilowatt hour produced, which is far below many other sources of energy. The level of cost that could be achieved, some evaluations show that we could reach LCOE of around $50 per megawatt hour, which is a good number. Some studies that were run by CATF in US show that the potential of superhot rock is huge. I have in mind the figure of around 650 to 700 times the electricity consumption of New York City.
Welcome to Geothermal Unleashed, where we're going to explore the cutting edge of geothermal energy. I'm Elizabeth Cambre from the Vallourec New Energies team, and I'm here to help educate and document geothermal's rise in the global energy transition. And I want to give a special thanks to Think Geoenergy. So I've got two guests joining me today. So first, we have Tony Pink from Mazama and Francois Penven from Vallourec. Today, we're going to be talking about superhot rock geothermal and the latest of what's happening in this space. And I want to give a warm welcome to both of you. And let's start by getting kicked off by talking about your backgrounds and how both of you got into geothermal. And so, Tony, why don't we start with you? So why don't you give us a detail on your background? Yes, go ahead.
Well, thanks a lot, Elizabeth. And I love the logo, and I love the title. So my background is I'm a driller of 34 years. And that was a career in Schlumberger and NOV in oil and gas. And in my last 3 years in NOV, I just started to realize when I was chief technology officer, the company was asking me, what's the next big thing? Yeah. And so I got into geothermal, and inside of geothermal, back then in like 2018, 2019, if you were in it, you realized it was starting to explode. But if you were outside, it was almost, quite silent out in the world. Yeah. And then what we have seen in the last 5 years is this exponential growth, with things like Forge project from the Department of Energy, with Fervo out there drilling, the New Zealanders pushing the boundaries. And then I got a really fantastic opportunity last year to support the Clean Air Task Force in looking at the gaps to get to superhot rock. And where I started in that project, thinking there were lots and lots of gaps and this was going to be really, really difficult. By the time I'd finished the report 9 months later, I was thinking, well, we can get on and do this. So I have my own business, which is Pink Granite Consulting, but the most exciting project I'm on at the moment is with Mazama Energy out where we have a rig on location today, and we will be drilling in January a well that will have a bottom hole temperature of 325, and then next year we will push that boundary to over 375, 400. Yeah. So thanks a lot for inviting me today, and I'll hand over to Francois.
Okay, thanks, Tony. Thanks, Elizabeth, for inviting us to this webcast. So about me, I'm a mechanical engineer from background. I've been working around 7 years in the automotive industry in various roles as project manager, as in quality field as well. And I joined Vallourec around 17 years ago. I had different roles at Vallourec, such as I was auditing the licenses who are machining the connections. That was my first role. Then I moved to a technical sales role. And finally, I had different role as a product leader for connections, but also for material grades. And recently, I moved to around 3 years ago to the geothermal environment. So Vallourec created a new entity, which is called Vallourec New Energies, focusing on 3 main markets: geothermal, hydrogen storage, and finally CCS. And I'm part of the geothermal energy at Vallourec. For me, geothermal energy is just great because you can extract energy from the ground, from just beneath your feet. And I think now with all the technology we have, is this technology can be dispatched in many places on Earth, not only the Ring of Fire, as it was the case before. And for me, that's what is great about geothermal energy, is that it's scalable. It can be implemented in many places on Earth. And I think that's probably the most important, with a very low carbon footprint. But I'm sure we'll get opportunity to talk about that later.
So Francois, you mentioned some key things about geothermal. What in particular excites you about Superhot rock geothermal?
Okay, so I think I mentioned some advantages about about geothermal in general. As we mentioned, low carbon footprint. I think the estimated carbon footprint of geothermal ranks from 12 to 20 grams per kilowatt hour produced, which is far below many other sources of energy. Of course, coal or oil or gas, but even it's very competitive compared to wind and solar. Geothermal is a permanent source of energy. You do not rely on if it's the light, if it's day or night. You do not rely on the weather forecast for if you want to compare with the wind. So it has a load factor which is significantly high. So that's valid for any kind of geothermal. When it comes to super hot rock, I think main advantages is first, I would like to give a rough figure, is when you consider a well at around 400 degrees Celsius, as Tony mentioned before, you can extract 4 to 8 times the same amount of energy as if you would operate a well that would run at around 180 to 200 degrees Celsius. So I think first benefit is this huge quantity of energy that you can harvest from the ground compared to more classical geothermal. I think that's a key factor. Then the second one, I would say, would be that it could be dispatched and deployed in much more region on Earth. So you do not necessarily need to have water aquifers underground. You can just extract the heat from the hot rock that is underground, and you are not or less depending on the underground. And I think that's also a very important factor, which means that it can be deployed in much more region or much more places on Earth.
That's great. Thank you so much. So Tony, when we look at what Mazama is doing in the Northeast with the recent project, how does this particular project in Superhot rock differ from past projects that have been done in the area?
You know, Elizabeth, that's really, you know, it's you know, Francois really set that up. Yeah. You know, the biggest difference is obviously the amount of heat that we can extract out of it. But over the last 5 years, as we've looked at geothermal opportunities around the whole globe, you know, we realized that even though there are super hot rock assets associated with hydrothermal, so that's naturally produced formation fluids, or as we say in the new IADC classification, we say reservoir dependent geothermal. Yeah. So if you look at that, what super hot rock does is it really enables us to go to the what we would call EGS and AGS type wells, where we're mining the heat and we're creating the heat exchanger ourselves. And what this does is it now says that, you know, 30 or 40% more of the globe is applicable for extracting this energy. We don't have these tiny, tight little geological provinces with uncertainty of fluid production and unique faulting and permeability. We have a much more broad canvas where we say, okay, I've got at 6,500 meters, I have 400 degrees C. if I put a well down there, I put a second one, and I in one way or another, not, it could be EGS, could be AGS, it could be we create a human created downhole heat exchanger. We change the whole footprint of this and make it much more global. You know, we have a very low heat gradient in UK. France has the similar challenges, but still, if we can push wells to the depth, you know, even though we have no hydrothermal significant super hot resources, we can probably create a super hot heat exchanger in both countries. Yeah.
Okay, so can you explain more about how you create the super hot
Yeah.
heat
Okay.
exchanger? Yeah.
Yeah. So obviously, what's really changed recently has been the sort of some big technological jumps on that journey. Yeah, you know, so we've got to drill just like an oil and gas well, a telescopic well bore down to a depth, create a horizontal section in very hot conditions. We have to complete that well in very hot conditions, and then fracture that well or fracture the producer to the injector, or the injector back to the producer, or both. And that's how we would create that heat exchanger if we're looking at EGS. For the sake of completeness, what we can do is also connect those two boreholes together downhole and create a closed loop system. But we have to create a lot of borehole to be able to create a heat exchanger that is going to have sufficient volume to produce heat. But maybe we can produce supercritical fluids, but not quite at the same volume as EGS. Yeah.
Okay, that's a great answer. So, Francois, can you talk a little bit about why Vallourec has made superhot rock part of its geothermal strategy?
Okay, thanks, Elizabeth. So first, maybe good to mention that Vallourec has been involved in various operations in oil and gas, for example, to harvest energy from the underground. So first, Vallourec has the knowledge about tubular technology. Tubular means metallurgy of what the metal is composed of. That one part. And our another expertise at Vallourec is also the ability to develop connections that are suitable for a given environment. So we have this expertise that has been acquired years after years in the oil and gas industry. So then I mentioned earlier our wish to pivot and to develop our expertise in new energies, especially the geothermal energy. And as we mentioned earlier, we clearly see that super hot rock is one of the key fields where that can deliver more energy, but also a field where, and Tony mentioned it just before, all the challenges that are associated to it. And I think Vallourec has this kind of DNA to be involved in challenging projects. This means being involved and engaged with the operator, with the expert of this activity, to really truly understand the challenges. And we have a strong R&D that can develop solutions, as I mentioned, both on materials, connections, but also associated services that can support such challenging projects. I think we have to be clear, and Tony mentioned it already, that many challenges are ahead of the road. So if we want to develop safely a reliable way to harvest energy from super hot rock geothermal wells, we are speaking about 400 degrees Celsius temperature. Just to compare, oil and gas maximum temperature is 240, 250 degrees Celsius. So we are here speaking about temperature which are at least 150 degrees Celsius beyond what has been done in oil and gas. So that's temperature in itself is already a challenge. Then at this level of temperature, the steel doesn't behave the same, connections doesn't behave the same. We have several parameters that need to be taken into account, such as material expansion, such as thermal derating of the material, and so on. And all of this need to be considered I like the motto that we cannot skip the physics. We have to consider what happened in the materials, what happened in the rock, what happened. And as Tony mentioned, we need a collective work to truly understand all the challenges and find solution, reliable solution to work on it. And I'm convinced that Vallourec has again the DNA to work on this kind of challenge. And we also see a value in it because we can harvest a lot of energy from this Superhot rock.
Thank you. So I'm really curious. You mentioned, Francois, that there's challenges.
Yes.
And Tony, so Mazama's just going into this with there still being potential technology gaps. So can you talk a little bit about what those gaps are? And then how is Mazama going to tackle these challenges?
So what I wanted to do is add one more thing to what Francois said.
Okay.
Is, everything that Francois had said is absolutely true. But this also has to last 30 to 40 years after we've put it in the hole. So everything that a Vallourec are that have the competency and the experience in making these connections and tubulars, and that experience, we need to extend it even further, because the designs of these holes have to last significantly longer than oil and gas. But, at a lower temperature scale, though, we put a system in place under Paris, and I think it was designed for 25 to 30 years, and it's still chugging along nicely after 50 years. So we can do it. Yeah. So back to Mazama. Yeah. So yeah, I mean, as we engineer every component of this project that's coming up, what we see is that there's a path through. There are some things that are close, that are tight, but nothing different to probably the first ultra deep well drilled off the Gulf of Mexico or something like that. By putting robust engineering practices in place, so I'll give you some examples. Yeah. So when we first looked at to be able to drill the wellbore 2 TD, we have to maintain the temperatures of the fluids pumping down through the pipe below the operating temperature of the weakest link in the system. So typically that's the electronics in the MWD. So current oil field electronics are 175 degrees C. So when we initially modeled the well, the bottom hole temperature with just naked pipe, was over 175 degrees C. So we can't drill it. Then we started looking at, okay, so if we put a pipe in there with a low heat coefficient coating on the pipe, and you get down to a little bit closer to 175, then you look at the surface system and you go, well, what happens if I put mud coolers on the surface, or mud chillers? Yeah. What if I get lucky and I drill in the middle of winter and the temperature outside's -10? Yeah. And then what happens if we put a bigger pipe in the hole? So we go from 5-inch pipe to 5.5 to 5 7/8. And all these little tiny silver bullets add up to a system that can actually deliver what we want. And it was very interesting. I had a conversation with one of the major oil and gas operators, and talking about these sort of topics, and they were like, we don't see how you can do it. And I basically had to say to them, I said, go away and do the maths yourself. Don't listen to me. Go and sit down and do proper well engineering calculations. And here's the thermal capacity of these things we're using. So they went off and did the maths and come back and they go, oh, it's actually all right. I go, yeah. You just got to do your homework. And so, yeah, we've had to look at it, Elizabeth, as a whole system, and treat it as a whole system. And once you do that, we're getting down to the temperatures where we have almost normal, but we have enough of a safety margin to do what we're doing. The other thing that is working in parallel to that, there are a couple of people out there. There's some technologies One is taking an MWD and you put basically a sub behind it, and the inside of that sub has been cooled in liquid nitrogen, and it transfers the coolness down to your MWD tool, and that can give you 60 hours of extra life. And there's now a startup who hope to have 210 degrees C capable tools ready by the summer. So you add that all together and you go, oh, okay, we will be, it'll be tight, but we can get there. And we've done the same for cement. We've done the same for casing design. You know, it all takes some hard, tough engineering, but very similar to looking at the tensile loads that were required to drill super deep off drill ships in the Gulf of Mexico. It's just some good solid engineering. Yeah.
Okay, so this year you're drilling a well that is 325 degrees Celsius, you said, and then next year you're targeting above 400 degrees Celsius. So
Correct.
are there going to be big differences in how you tackle the design of each of these wells?
I have to be careful on how much that I reveal. So
Okay.
fundamentally, we're engineering what we're doing this year with what we need to do next year. So we will be having products that are going to enable us to drill next year's wells, going in the ground to see what the impact of those products are at the cooler temperatures of 325, where we have much lower risk. So, you know, we'll be testing a number of things like insulated drill pipe. Yeah. So a double skinned drill pipe that will give us a good indication that when we do drill those longer wells in 2025 and 26, that we have technology that will get us to TD in a relatively low risk way. Good
Okay.
question. Yeah.
Okay, so Francois, you mentioned before Vallourec is doing work on connections, looking at material. Can you expand a little bit more about some of the R&D work that Vallourec is doing specifically for superhot rock geothermal?
Yes. Okay. So several things. First, I think it's key to truly understand the way materials behaves at that level of temperature. So one very important direction where Vallourec on which Vallourec is working is to develop our true understanding of how material behaves at this level of temperature. So our R&D teams have spent times to analyze the classical OCTG materials and to characterize accurately how they behave in terms of temperature derating, creep, thermal elongation, as well as a response to cycling, temperature cycling combined with load cycling. And that's very important. That's a very important base to understand how our connections will work at this level of temperature. So that's one key parameter. Then second, so our pipes, unfortunately, are only 13 to 15 meters long. So we need to connect them. And over the last 60 years, we have developed several types of connections which address the different markets and the different challenges our oil and gas and now geothermal customers are facing. So we have test benches. We have developed test benches to test and to qualify the connection to the various environments to which they are confronted. And then we have recently as well work on how to improve and to increase the capacity of those test bench. As I mentioned earlier, oil and gas, the tests were done up to 240, 250 degrees Celsius. Now we are speaking about right now 350 degrees Celsius, but for super hot rock, we are targeting 400 and maybe in some case 450 and maybe higher in the future. So we have to make sure that our test equipment are able to operate at higher level of temperature. So that's the second direction. Then the other one is that we need, and I think that's very important, to understand what happened to all the pilot projects that have been drilled at high level of temperature. So several high temperature geothermal wells have been drilled already in Iceland, in other regions of the world. They have faced challenges. So I think the good news is, first, it has demonstrated that you can harvest a huge quantity of energy. I have in mind the figure of 36 megawatts that was harvested from one well in Iceland. Unfortunately, and as Tony mentioned earlier, it didn't last long enough. So it was only a few months because so many challenges happen in that well due to the condition again. But we can draw many lessons from all those experiences. And I think it's important to analyze in details what happened to all those different operations and to truly understand every single failure and to learn from this failure to develop solutions that will be able to handle all those conditions and to avoid those failure modes. So I think working on the failure modes and lessons learned from past hot temperature geothermal wells everywhere in the world for me is key, and that's also something we are doing. And I think to jump on one of Tony's comment earlier is that I think in this space collaborative work is key. So it's not a scientist working alone in his lab or in his testing facility or whatever. We need to talk together because the knowledge is not captured in only one brain. It's fragmented in different brains, and we need to have all those experts working together, talking together to find, to understand and find solutions to address the challenges. And I think with that regards, the workshop that CATF organized in US a few weeks ago was great because it was a good opportunity to gather people with different backgrounds, having different experiences in different fields. And I think that's really the way to progress the technology on the various fronts. And Tony mentioned challenges for the drilling. We have challenges for well constructions. Others have challenges at the surface. And all of this needs to progress at a similar pace to have a robust technology at each level of this super hot dry rock development.
Yeah, I completely agree. What was really nice, Francois, was that there was actually strengths in different areas. Yeah, it looked like the New Zealanders were really strong on geochemistry, changes in the rock, fractures, deposition of minerals along those fractures. It looked like the US contingent were really looking at the well construction and ROP generation. And then the Icelandics were, looking at how do we prove it out quickly? What's the pathway to doing it? Because they obviously have, heat at very shallow depths so that we can test things without having to drill 6.5 kilometers to get there. So no, it was really cool. I really enjoyed it. Yeah.
I love that summary of how you describe collaboration in the geothermal space across the globe. That's pretty exciting. So one thing I want to ask is about the economics. Tony, can you talk a little bit about the efficiency of Superhot rock and the cost benefits that come along with it?
Yeah. I mean, Francois touched it at the start, but because of this 4 to 6 times extra energy output, that just gives you such a good, that side of the equation is so healthy. So the other side of the equation is how much is it going to cost us to do this? Yeah. And I went through a really interesting exercise over the last couple of months, which was that the challenge was to express this to the C-suite of oil and gas companies. Yeah. So if I want to explain the economics of super hot rock drilling to a CEO of an oil and gas company, how do we do it? So I kind of started looking at it. Right, I'm going to look at a shale field. Yeah. And I'm going to convert the super hot rock into barrels. Yeah. So we looked at the barrel output, and a good super hot rock well would produce 225 barrels a day. Now that doesn't look like a gusher, yeah, from an oil and gas perspective, but after 30 years, it may still be producing 190 barrels a day. So then you look at the shale economics and you go, well, okay, if I want to maintain that production, I'm going to have to drill 6 or 7 shale wells along the life of that asset to produce the same amount of oil. And then you look at 6 or 7 shale wells, which are going to cost you between 5 and 10 million each. And a super hot rock geothermal well is going to cost you 50 to 60 million for a pair. Yeah. Then you do all the maths and you look at the return on investment over 25 years, and the oil was still better. It was about 275% over 25 years. And the super hot rock geothermal was like 240, 250. And when I've presented this to, finance people, they've gone, oh, that's almost, statistical error irrelevant. Yeah. So they were very comparable. Yeah. And that's been one of the challenges for oil and gas people, thinking, oh, I'm not going to make the sort of returns on money. But I think they're starting to think now that I will have a fluctuating oil price for my assets. And then I can start drilling super hot rock geothermal and have a baseline of steady, producible revenue in the similar ballpark to their baseline oil and gas. And when the oil price is really high, they'll make more money. When the oil price is low, they'll be protected from that drop in price by having this high capacity super hot rock geothermal. So I'm hoping, and it's really interesting, Elizabeth, that every time you turn up to an event now, you just start to see a few more oil and gas people in the room, and I've seen ExxonMobil people recently, and then finally in London last week, there was a lady who asked me a question, and she said, "Oh, I'm so and so from Shell." And I went, "Aha! The last one to the party is here." So I think they're waking up to it, and that economic matching of the two, that's what I like the most about super hot rock compared to the lower enthalpy stuff. Yeah. There is heat geothermal heating projects that have good returns because the wells are so cheap to drill. But super hot rock and heating, I think, are the two sweet spots in it. And definitely for high capacity electricity production, I think super hot rock is the one to go for. Yeah.
Okay, I've got a burning question.
Go on then.
What do you think the growth of super hot rock is going to look like? Maybe, Tony, you can speak about it in the US. Francois, I don't know if you have any insights to share on what you think globally it will look like. I mean, do you think we're going to see 1 or 2 wells drilled a year? Or do you think we'll see more companies entering this space?
So I'll give a quick. I think that there will be. We need some big successes for sure.
Okay.
Yeah, same happened in shale when once the fracking and the reliability of fracking, shale took off and exploded. Yeah, so we need some solid successes for sure. So some setbacks in that will delay, but fingers crossed. Between Mazama, the New Zealanders, Icelandics, and maybe some other countries who dive in there, we'll have some solid success stories, which would be really cool. And then I think there is the desire, the need for it is picking up as well, because the data center, artificial intelligence, and the people that run those companies have an enormous amount of capital available. And they're starting to feel a little bit guilty about the amount of energy they're consuming. And super hot rock geothermal not only gives them electricity to power their data centers, but through doing heat transfer, we can take that heat energy and convert it into cooling and keep the place. So we can use the data center to cool down our fluid to improve our economics of our actual electricity production. So I think you'll start to see artificial, data centers and super hot rock drilling tied together, because you can put the data center right next to because bits are easier to transfer than electrons. So I think those two will catalyze the industry. Yeah, I think it'll grow faster than people think. I am very positive. Always a positive. Anyone who knows me knows I am a very positive person, though. So, yeah.
I love hearing that. Francois, do you have any thoughts on that?
Yeah, so first, fully agree with what Tony said about the fact that we need a few successes to show that this technology is working, is reliable, and can deliver energy in a stable way. So that's clear. But I think that's the case for every type of industry. The first electric car, some people didn't thought it was possible. Now I think everybody's convinced. Oil and gas, the most challenging oil and gas project, like deep offshore, at some point there were debate about the fact that whether or not it was possible and scalable. We have various deep offshore wells, deep offshore exploration around the world now. So that's key point. We need to have some successes. Then I think some studies that were run by CATF in US showed that the potential of superhot rock is huge. I have in mind the figure of around 650 to 700 times the electricity consumption of New York City. So I think this figure alone shows that the potential is there. So if we have a reliable solution, it will be it could grow. And the level of cost that could be achieved, some evaluation show that we could reach LCOE of around $50 per megawatt hour, which is a good number. And I think this figure as well is interesting and convincing. And finally, we need to have access to, I think, as Tony mentioned, several industries need to have access to significant quantity of energy, but on top of that, they need stable prices, and they need stability of supply. And maybe another perspective here in Europe, when the crisis in Ukraine started, the cost of gas went up by many percent. So the cost of energy raised significantly, and every industrial activity realized that having security of supply of energy at a stable cost is an important factor. And I think geothermal and superhot rock in particular can deliver this stability of supply and stable prices, which is again just below your feet. So it means you do not rely on a network or external supplier or whatever. And I think that's also an important factor.
Yeah, I think Francois is absolutely right. Stability, and I think stability is sort of not given the recognition that it needs. Yeah, everyone wants us to be cheaper than natural gas, or cheaper than nuclear or whatever. But it is all of that with no waste, very little footprint, low carbon footprint. But that stability, it needs to get shouted a little bit louder on that stability. That's why we're here on a podcast shouting. Yeah.
Well, I want to thank you both very much for joining me today. And I want to thank the listeners for joining us on this episode of Geothermal Unleashed. And I hope today's discussion has sparked new insights and deepened your understanding of the geothermal industry's incredible potential. Until next time, keep pushing the boundaries of what's possible, and let's continue working together to unlock the full potential of geothermal. Thank you.